Hello and welcome back to Differential Equations, section 5.2 on the eigenvalue problem for homogeneous systems, meaning the ones that are equal to 0, right? So, eigenvalue, What's the eigenvalue? Well, it's German, right? And the word eigen refers to the one. Okay, the one, the special solution. Now, if you can learn this as a procedure and just go through it and most of calculus and get your grade, or you can try and understand what that actually means. Now, in linear algebra, there is a whole chapter devoted to eigenvalues and eigenvectors. And we are going to kind of mush that into one section and apply it immediately to differential equations. So, what is the idea of the word eigenvalue or eigenvector and so on? So, possibly the best thing to understand would be the eigenvector, and then also there is eigenfunction, which is also a great example. So I will give you an eigenvector example first. You can have a system in space, and when I say system in space, you can literally think any 3D object that crosses your mind. But I want you to imagine that object that it's made out of clay or some material that you can deform, right? But it has to be a solid object. So you can't use water, you can't use sand, you can't use anything that will, lose its shape on its own, right? You need a solid object, and then you have to bother it to deform it. Now, what I want to do is I want to deform that object by squeezing it, pressing it, bending it, whatever. And what I'm looking for is a part of the object or the line within the object, or some part of the object which will stay unchanged even when I deform the shape. So let's say you have a rectangular block, like a box or something, but it's made out of clay. And it's sitting on a desk, right? And it's sitting on that surface on the bottom, which is a rectangle or a square or whatever. Now, you twist the top, and now it becomes this twisted prism, but the base is still the same shape as before. So, transformation happened to the object, but the bottom, in this case, the bottom stayed unchanged. I could have the same shape, and hold it in my two hands and then twist, in which case both shapes at the ends would rotate and change, but the one in the middle would stay the same, so that would represent the eigenvector. So the meaning of the eigenvector is something that stays in a system, something that stays unchanged under transformation. So when you do matrix operations, it says unchanged. Now, the best example of all, forever and ever and ever, will be calculus example of derivatives and integrals, because, believe it or not, we can actually define matrices, transformational matrices, that will do differentiation, integration, and so on, right? If you talk about linear space of functions, so you're talking about functions as entities in linear algebra, function e to the x would be the eigenfunction, the eigenvector, right? That would be the one, because when you apply transformation called the derivative to it, it stays unchanged. And if you apply integral to it, it stays unchanged. So those of you who want to understand what the meaning of eigenvalue, eigenvector, eigenfunction, right? The meaning is simply, once you bother it with whatever transformation it's coming, whether it's multiply by another matrix to rotate or deform, or multiply by another matrix to take the derivative or integral, because those can be defined to do those operations. What is that one vector or one thing that stays unchanged as you, right? You can also think about addition, right? When you add a 0, you still have the value unchanged, right, and so on. So there are a whole bunch of things that you can think of. So what is that we are dealing with today? Well, the matrix approach to all of this, the linear algebra approach to all of this, is literally just to bring in multiple equations, multiple dimensions to the one-dimensional problem we had before. Before, in a first-order linear system, we assumed the solution of e to the t, or e to the kt, or whatever, and then we went through a procedure to figure out what that k is. Then, when we had the second order, you guys had characteristic equation with r, and then you figured out, when you had two separate real solutions, that you had e to the t and e to the a1t, r1t, and e to the r2t, right? So that was there. So now we are going to assume again the same thing, except we are going to call it e to the lambda t, which is another Greek letter lambda, and that lambda will be called the eigenvalue, and that lambda will be calculated using this procedure that we are going to learn in this lecture. So we are going to start with the generalization of all of this when you are starting with your system. X1 prime is equal to a11 x1 plus a12 x2 plus a13 x3 plus ... going all the way to a first, a1n xn, and then the second order, right, a21 x1 plus a22 x2 plus a23 x3 plus ... plus a2n xn, all the way down to, and now remember, this has to be a square matrix because the number of variables has to correspond to number of equations. When I say variables, I mean variable functions, unknown functions. So what used to be x, y, z number of functions, now we're just using x1, 2, 3 for simplicity. So we have xn. So it used to be in the first lecture m and n because we could have rectangles. Now we have to have squares. So an1 x1 plus an2 x2 plus an3 x3 plus ... plus ann xn. So that is our system of any order. 3 equations, 4 equations, 10 equations, whatever. So we have to write it this way. With its associated, now it's homogeneous because, see what's missing? Plus f1 of t plus f2 of t, right? That's missing. That's not there, which is why it's homogeneous, right? It's plus 0. So the solution would only be the xc solution, right? So we'll just call it x of t, and that's a vector, obviously, because that's all of the x1, x2, x3, and so on. So that's c1 x1 plus c2 x2 plus c3 x3 plus ... cn xn. So these are all of our solutions, and now we are going to so the solution technically works the same way as it did before. So I'll just say solution. I will box this. Maybe I should make a separate box for the solution. There we go. So we have the system and we have the solution. Let's do it this way. System and solution. Nice. All right. Not nice. It's terrible and ugly and disgusting, but whatever. So now I am going to do what we did what we did before. We can create the system, and we can do all of that stuff. But first, what I'm going to do now is I'm going to assume, as we assumed before, that all of these are linearly independent. They don't have any repetition. They're not going to work out to be complex or anything like that. So I'm just expecting some kind of e to the RT equation, but in this case we're going to call it lambda. So my solution x of t, which was the good old x1, x2, blah, 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 xn, is now going to be written in this little weird notation, but I'll toss in x3 to match the book. This notation that we need to understand. So v1, that's a lowercase v1, e to the lambda t, v2 e to the lambda t, v3 e to the lambda t, dot 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 vn e to the lambda t. And as you can see, that all creates this vector v1, v2, v3 dot dot vn times e to the lambda t, which is going to give me v, vector v, e to the lambda t as a solution. So this is my solution, which is now represented in this way. And that will allow me to transform my system. Now they switched the notation on us. Right? It used to be px. Now they put a there. It's the same matrix as before. And when you now know that x bar is this vector v e to the lambda t, and you know that you can differentiate that one, that will drop lambda down, right? Because lambda is a number, like 7 or something. And you plug both in, you will get a lambda v e to the lambda t equals a v e lambda t. I did not specify this is lambda, Greek letter lambda, which is equivalent to our lowercase l, and this letter is used to denote the half-life, both in mathematics and video game half-life, right? So lambda is the symbol that you probably have seen before, especially if you are a gamer. So now we are going to, by the way, if you did not play Half-Life ever again, you are not a gamer. No matter what everyone ever tells you, you are not a gamer. You have to play Half-Life 1 and 2. That's, you know, that's like you say, oh, I'm an avid reader, but you never learned alphabet. So yeah, basically it's the same thing. All right, cool. So now when you look at this, you can divide both sides by the non-zero term, right? So you can divide both sides by e to the lambda t. And you will get this equation where I have a bad habit of dropping this arrow. AV is equal to lambda v. And now you will put these two on the same side. And here is the huge issue that we have, which needs to be fixed. That's a matrix. Can be 3 by 3, 100 by 100. billions and by billions for Google search engine, right? If you want to be high-end programmer, you have to know linear algebra and advanced linear algebra. Without those, you are going to be programming vending machines only. So if you want to work for Google and stuff like that, you can't do anything without linear algebra, because, you know, those are the matrices, all the compression files and everything else. All right, cool. That's a number. So we cannot subtract. We have to fix this. And there is a very easy fix. You will multiply the second term over here by the identity matrix I of the same order what A is. So if A is 2 by 2, you will multiply by the I2, which is 1, 0, 0, 1. If the A is 3 by 3 matrix, because you had 3 equations, you will multiply lambda by I3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have to fix this by multiplying IN into lambda V term. Right, that's what we have to do. So I'll just say matches the order of A. That should be enough. So now I have AV minus a lambda IV equal to 0. Now, if I put n by n over here, then I'll put in over here. So that should now make sense. And we can factor out v to get our equation that we are looking for. So this was all derivation. So what we get now is a minus lambda I times vector v is equal to 0. That's the big equation. So now we get to define eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So the number lambda, which could be 0, is called an eigenvalue of the n by n matrix A if determinant of A minus lambda I is equal to 0. Determinant. Guys, in these absolute values, you have a matrix minus matrix. So that's going to create a new matrix. And then when you have these around, that means you have to take the determinant. An eigenvector so we have the two keywords, eigenvalue, eigenvector. The eigenvector associated with the eigenvalue lambda is a non-zero vector v, that was the v that we have seen before, such that AV equals lambda V. This means that when you multiply matrix times a vector and the number times the vector, it gives us the same value. So that A minus lambda I times vector V gives us 0 matrix. This is your regular 0, which you know since the day you were born. This is your 0 matrix, right? 0 vector, actually. 0 matrix as well, whatever. Every vector is a matrix. It's just either a column or a row vector. Their matrices. You can have 3 by 1, 1 by 3. Those are matrices as well. Well, cool. That's the theoretical part. And now, when we did this, we can define the eigenvalue solutions. So yes, finally we can solve the systems from 5.1 with this. Now, I don't have anything that shines brighter than this red. So I guess I'm going to encase this into. So let's go with eigenvalue solutions. Of x prime equal ax. This is your differential equation system, right? So the solution is dx prime dt is equal to ax bar, has the solution given as ax bar of t is equal to ve to the lambda t. So there it is. Now we need to make sure that this thing stands out. How do I? It looks terrible, but is there any way I can make this worse? Of course. There we go. Now it looks even worse. Excellent. So if you ask how to solve systems, this is how you solve systems, right? Now you need to know the procedure. Now clearly we need to know the procedure to find lambda, to find v's, and then you will just put them together. The answer will look like all of those e's and stuff that we have seen before, right? That's our solutions. So let's start with a simple 2x2 case. Grind through the procedure, then do another homework example, and I think we end the class that with complex eigenvalues. Great, is gonna maybe bleed into next day, or maybe we'll see. Let's go. All right, so I have x1 prime to be 4x1 plus 2x2, and x2 prime is 3x1 minus x2. So we have a standard coupled system that has two unknown functions, x1 and x2. We are expecting those two as the solutions, obviously, and it's just all in all standard stuff. So now we are going to use linear algebra to solve this system. So we'll have our dx dt is equal to the matrix of coefficients 4, 2, 3, negative 1 times x bar. Now this one matches the system, right? What we are doing here. All right, cool. Now I need to calculate eigenvalues first, then I calculate eigenvectors, and then we are done. So now remember the way to calculate eigenvalues. To calculate eigenvalues, we are using A minus lambda I equal to 0. In this parenthesis, I need the determinant, right? So use this to compute lambdas. Why lambdas? Because 2 by 2 will give you 2 lambdas, 3 by 3 will give you 3 lambdas, 100 by 100 matrix here will give you 100 lambdas. All right, so what do I have? Well, this is my A. So I have my matrix A, which is 4, 2, 3, negative 1, minus the unknown lambda times the same order identity. I need I2. So this is a I2 because my matrix was 2 by 2. Now I have 4, 2, 3, negative 1 matrix minus lambda 0, 0 lambda. You will be skipping all these steps later, but it's good to write them at least once. Matrix subtraction is done location by location, right? So we are getting 4 minus lambda, and then 2, and then 3, and then minus 1 minus lambda. Maybe I should write equals 0 every time. So it's complete. So you will technically write this immediately because you see that you just subtracted lambdas on diagonal. That's the case every time, right? So we need to solve this, right? You know what to do. That's going to give you 4 minus lambda times negative 1 minus lambda minus 6 equal to 0. Now you have to FOIL here. If you multiply both of these parentheses by negative 1, this is a trick for quick calculation. So if I say times negative 1 and times negative 1, it will give you a little bit easier, right? And times negative 1 is going to swap the order in the first, and in the second is going to put them all to be positive. Change all the minus into positives. Probably this is the only thing that's going to trip you over because the rest is calculus. You're good with that, right? The algebra is, run for your lives. So we have lambda squared minus 3 lambda minus 4 minus 6 equal to 0. Condenses into lambda squared minus 3 lambda minus 10 equal to 0. Factors into negative 5, positive 2, lambda negative 5, lambda plus 2 equal to 0. And here we have our two eigenvalues. Lambda 1 equals to 5, lambda 2 equals to negative 2. Okay, and now for the tough part. To find eigenvectors. Usually that's the one that it's a little bit annoying, but it's doable. Just pay attention. It's doable. Lambda 1 is equal to 5. We need to solve the system to find the eigenvector v so that the answer is 0, 0, because that's what we, if you go back and remember, well, here is the formula we're going to use. It was, right here. This is what we're using. So we're going to plug in our lambda, compute the matrix, set this up as V1, V. They're using A and B in the book. You can use V1, V2. I used V1, V2, V3 when I was taking the class. And we are shooting into a zero vector. So we need to find those two values. So when lambda is equal to 5, we have our matrix from before, lambda minus 5. So this is going to be, it's this matrix here, guys. So 4 minus lambda, and then 2, and then 3, and then negative 1 minus lambda, and that needs to be multiplied by this column vector. They use A and B in the book, that's fine, and that needs to give us 0, 0. So from A minus lambda I times vector V equals 0 vector. So this can be of any order. Can be of any order. So plug in 5. And we get negative 1, 3, 2, negative 6 times A and B equals 0, 0. Okay, I'll write it now. Need to find A and B. So the equation holds. Meaning, you can't just put anything. You can't put 7 for A, right? If you put 7 for A, then and 7 for A and 1 for B, you're just going to have negative 7 plus 2, and that's not 0, right? So you have to pick A and B so they give you zeros on the other end, right? So that's something that it's important. So what do we have here? Well, we have the system that you guys are used to, right? Which is negative A plus 2B equal to 0, and 3A minus 6B equals to 0. So now, there are infinitely many solutions. You just need to find one. Any one works. You can pick your A or your B to be a value. Let B equals to 1. It doesn't matter. Pick A to be 7. I don't care. Just pick something, right? And plug it in. So if you have the value for that eigen, right? So if B is equal to 1, then negative A plus 2B equal to 0 will turn into negative A plus 2 equals to 0, and then A equals negative 2. No, A equals positive 2. Try it in the second equation. See what happens. right? 2 times 3 is 6, minus 6 is 0. It works in a second equation as well. So, we found our first eigenvector. When a lambda 1 is 5, my first eigenvector v1 is A is 2 and B is 1. That is going to give me my first x1 solution of two, 1, x bar. I mean x the arrow. Actually, e to the 5t. Remember how all of these were given to us in a 5.1? And I think, Mike, you asked me, how do you get these? Well, I'm finally able to answer your question 48 hours later. Better late than never, right? Great. Now lambda 2 was negative 2? Yep. Plug negative 2 in the matrix. We have 6 and then 2 and then 3 and then negative 2, that's positive 2, so 1. Times A and B equals 0, 0. It creates 6A plus 2B to be 0. 3A plus B equals 0. Easy equation is here to say that, I mean, you can pick any. Do you see that they're constant multiples of each other? They're always constant multiples of each other. So you just pick one value for one of the equations and the other one you compute from any row and you're done, right? So if I pick A equals to 1, then B is negative 3. So I have, guys, there are infinitely many solutions. I could have picked A equals to negative pi. It will still work. All right, so it doesn't matter what you pick. Just for one of these 4 letters, pick a number and compute the rest. Now, my experience is that I know what I should pick. I look for the equation that has a single, right? And then I pick the other one. I don't want to pick a single because if I pick a single, then I have to divide by 3 to solve for A. So I find the row that is single and then I pick the other one. You don't have to do that. You can literally pick whatever you want. You can go and pick here A to B7 and go from there. It doesn't really matter. So now we have that our lambda 2 is negative 2 and our v2 vector, eigenvector, is 1, negative 3, which gives us the solution x2. I forgot these arrows again. To be 1, negative 3 e to the negative 2t. Hey, there they are. So what's my x bar, x solution? What's my x solution? C1 times 2, 1 e to the 5t plus C2 1, negative 3 e to the negative 2t. Basically, this will later on become your xc. There will be xp to find and so on. All right, cool. So now I have this. What now? You have the Wronskian that you can check. There could be initial conditions that you can find. You can write it in the separate solutions. X of t is 2c1 e to the 5t, what we practiced in a previous lecture. You can write them as separate equations. You can do that. If you have initial conditions, you work out initial conditions, right? If you have 3x3 system, this whole thing is way more annoying to compute because you have to find determinants of 3x3, calculate the vectors for 3x3. Well, we're going to do an example now, but I just need to make sure that you understand that you can have the repeated solutions and you can also have the complex solutions for vectors, which will give you, right, because this solution is when I had two real, right, in the exponent. But remember that it can be repeated and it also can be complex. So all of that stuff now is going to be also in a system. Let's first do the 3x3 case. And see what that looks like. They give you about 10. And I'm just going to pick at random. I'm going to do 18 because there is another example. Yes, here's another example, but this one is with 3x3. X prime of 1 is x1 plus 2x2 plus 2x3. If I mess up copying any one of these, 2x1 plus 7x2 plus x3, holy nightmare, and x3, 2x1 plus x2 plus 7x3. So x1 plus 2x2 plus 2x3, 2x1 plus 7x2 plus x3. Holy nightmare. Okay. Let's see if we can get through this mess without messing things up. All right. So we have, this is our derivative. Our matrix A of coefficients 1, 2, 2, 2, 7, 1, 2, 1, 7 times the vector x, which is x1, x2, x3. So this is our system, right? So that thing is the definition we had. Oops, I don't need a prime and D notation. It's one of them. Right, so that's that part, and we were able to make it to look like this. Now our job is to find eigenvalues, right? So we're looking for eigenvalues. So we're going to have the determinant of 1 minus lambda 2, 2, 2, 7 minus lambda, and then 1. And then 2, 1, 7 minus lambda equal to 0. That equation there is your A minus lambda I. I have this bad thing to put the parentheses instead of absolute values. I don't know why. It's a determinant. So now we have to find the determinant, which is going to take about a year. We have, remember, pivot, and then we do this, right? So we start with 1 minus lambda, and then in this parenthesis we have 7 minus lambda times 7 minus lambda minus 1, and that's for the first one. Then you have the minus in the formula, when you jump to the second one, which takes out a row and a column. So minus 2. And in parentheses I have 2, 7 minus lambda minus 2. Finally, plus 2 when I work out the third one. And over here I have 2 minus 2 times 7 minus lambda equal to 0. That's it. Best way to learn this procedure is just find some victim and preferably know nothing about math and just explain this to them. The whole procedure, top to bottom. What do we have here? We have 49 minus 2 lambda plus lambda squared minus 1 minus 2 times 14 minus 2 lambda minus 2 plus 2 times 2 minus 14 plus 2 lambda equal to 0. I'm gonna get cross-eyed over here because I am keeping one eye on the chat to tell me when I make a mistake. Not if, but when I make a mistake. And I'm trying to solve this at the same time. 1 minus lambda. This is now lambda squared minus 2 lambda plus 48. Minus 2 times 12 minus 2 lambda plus 2 times negative 12 plus 2, so 2 lambda minus 12 equal to 0. Shouldn't it be negative 14 lambda? Negative 14 lambda. Yeah, I am so lost now. I'm not sure if you're talking about line 1, 2, or 3. Shouldn't it be negative 14 lambda? Yeah, the last two boxes should cancel out. (14) minus 2 lambda minus 2 2 minus 14 plus 2 lambda. Line 2 part 3, so I think you're talking about this term here. 2 negative 14 plus 2 lambda. 7 minus lambda, 7 minus lambda. Seven minus lambda is a minus b squared. The formula for that is a squared minus 2ab minus b squared. So, oh, this one over here is 7 times 2 is 14. There, oh, okay, now I see it. Yep, got it. What do I do without you guys? Thank you. Alright, well, that would definitely make a lot of noise. Oops. So now we get to FOIL. I hope everything else is good. When you said part 3, I went part 1, part 2, part 3. So, okay, now I get it. Okay, so yes, 49, 7 times 14 times 7 times lambda is 7, lambda times 2 is negative 14, and then lambda plus lambda squared minus 1 gives us 48. The rest should be good, and it's time for us to distribute and FOIL and do all of that stuff. So now we have 1 times lambda squared minus 14 lambda plus 48 minus lambda cubed plus 14 lambda squared minus 48 lambda minus 24 plus 4 lambda plus 4 lambda minus 24 equal to 0. I don't need these parentheses here because don't change anything. Like terms, negative lambda cubed. Now all of the squares, I just have plus 15 lambda squared. All of the single lambdas, single lambdas. I think that's it. Yeah, that's it. The 48, 24, and 24, they cancel, which is nice. So over here I have 14, 48 gives me 62. So negative 62. And then I add 8, which is subtraction. So that's 54. I just hope that this is all good. What a mess. What a mess. So negative lambda cube, lambda square, and plus 14 lambda is 15 lambda squared. There are no other lambda squares anywhere. And then 8, this will just make negative 6, negative 54. Yeah, it looks good. Let's say it's good. So what do I factor here? I'm going to factor negative lambda and leave it with lambda squared minus 15 lambda minus 54. So I factored out negative lambda, and for now I have negative lambda equal to 0, which is lambda equal to 0, because lambda can equal to 0, right? And now I have the other one, which I use quadratic formula for if we can factor. Factoring might be easier, but not everything factors, right? So what are the factors of 54? I'm just going to really quickly run through this. So 1 and 54, 2 and 27, 3 and 1 and 18. Oh, that gives 15. So that's a negative and a negative right there. Great. So it factors over lambda plus 3, lambda minus 18. So that gives me lambda 1 is 0, lambda 2 is negative 3, lambda 3 is positive 18. Good. Uh-oh, something else is wrong. You said negative, positive. Wait, what do I have here? I have negative lambda, negative. Ah, that's a negative. That's a negative, right? Because it's a negative and a negative and then a positive. So that gives a negative. So that's going to be a positive here. Yeah, that ruins everything now. So positive 54, and I need negative 15. Oh no, wait, somehow I got it. And then, all right, cool. So this doesn't work anymore. Doesn't work anymore. So, well, that's it was so nice. Oh, 6 and 9. Yes, 6 and 9 to make 54, and then both negative. So lambda minus 6, lambda minus 9. So lambda 2 is 6 and lambda 3 is 9. Yes! Oh, all right, cool. I'm so happy. We're actually going to finish this problem today. We are. So where lambda is equal to 0, we go back to our matrix and put lambdas to 0. I am going to copy this matrix so I don't have to scroll up and down too much. Put it over here somewhere. Okay, so actually I don't need this, I just need the matrix. Let's put blue. And move it to the side. All right, so I'm placing it down because I still need to do lambda 2, lambda 3. So when lambda is 0, all of these become zeros. So my matrix is going to be 1, 2, 2, 2, 7, 1, 2, 1, 7 times ABC, giving me 0, 0, 0. So when lambda is 0, this is my matrix. Solving this matrix now is a little bit more involved than before, because I have to solve the system down to have one variable and then bring that one back for others. Could you use any lambda? You have to use all lambdas. You have to use all lambdas. So we are going to have 3 separate calculations. So first lambda is going to give you the first vector, and that's going to be for your x1. Second lambda is giving you x2, and the third lambda is giving you x3 with their associated eigenvectors. So the number of equations is the number of lambdas, and that's the number of calculations for eigenvectors. So, yeah. All right, so what do we have here? We have a plus 2b plus 2c equals 0. 2a plus 7b plus c equal to 0, and 2 plus 2a plus b plus 7c equal to 0. So that's our life now. And we have to eliminate any of these. So I'm going to multiply the top by -2 and add into equations 2 and 3 to kill a's. So when I multiply by -2, that becomes -4 plus 3 becomes 3b. -4 plus c is -3c equal to 0. So -2 and positive 2a cancels. -4 plus 7 is positive 3. -4 plus 1 is -3. Good. Now do the same with the 1 and 3. We have -2 times a, and this cancels. -4 plus 1 gives me 3. No, -3b. -3b. And then when I have -3b there, and then I have -4, this plus 3c. Okay, good. Look, they are constant multiples of each other. If you want to, you can divide each by 3, and you get b minus c equals 0 and negative b plus c equals 0, which clearly, right, tells you that b is 1 and c is 1, right, to get these zeros, right? You have to have b is 1. Can you have b 5 and c? Yeah, you can have them to be 5s or pi's or whatever, right? They have to be the same number. Once you have b and c, bring them back up there to figure out what your a is. So your a plus 2b plus 2c needs to be 0. So a is clearly negative 4, right? Because they need to add to 0. That gives you your first, here's the new word for you, eigenpair. That's a new word for you, of lambda 1 is equal to 0, v1 is negative 4, 1, 1. All right, rinse and repeat for lambda 2, lambda 3. We'll have to continue this lecture on Friday because we haven't touched the complex roots yet. So, and it's already 12:54. So I'm just going to finish this problem. I know I'm going to go over time. I'm going to finish this problem and then we'll finish this lecture next class. So now lambda is 6. Remember that I brought this matrix so I can quickly refer to it rather than scrolling all the way up. Just bring the matrix down. We can just look at it. No, that's supposed to be blue. So what do I have? Plug in these. Lambda is 6. So I have negative 5, 2, 2, 2. When lambda is 6 is going to be 1, 1. 2, 1. When lambda is 6, that's a 1. That is a matrix times the matrix of A, B, C to give us 0, 0, 0. That is when you do matrix multiplication, right? So row times the column, that gives us negative 5A plus 2B plus 2C equals 0. I'm not sure if I mentioned this. We did matrix multiplication, but the way it works is this and this, right? So negative 5 with A, 2 with B, and 2 with C to give you the 0 that it's there. That's the way matrix multiplication works. That was Monday's class. All right, cool. So now we're going to go down and go 2A plus B plus C equals to 0. And 2A plus B plus C equals to 0. Oh, look at that. Isn't that the same equation? So let's see what we need is we can eliminate C if you want to. So times negative 2 times negative 2 to eliminate C. And we'll go from there. So you're going to get, again, two equations, so you don't really need to write this twice. You have your negative 5. When I multiply by negative 2, sorry, hold on. Negative 2, that's going to give me negative 4, so negative 9A. When I do negative 2, that eliminates my B and eliminates a C. And that's going to give me that A is 0. And then we can pick B and C to be negative 1 and positive 1, right? Perfect. So anything that works, any witchcraft that you can pull off to come up with numbers that will work in all three equations to give you zeros. If you can do guess and check method, you know, throw some bones in the fire or whatever your method is, just get this V. V2 is, in my case, 0, 1, -1 because it works. So we have another eigen pair of lambda 2 is 6 and the vector V1 0, 1, -1. Keep forgetting these arrows. Cool. Lambda 3. The light at the end of the tunnel over here, right? We're taking away 9 now, so that's going to be -8, 2, 2. -9, so 2, -2, 1. And 2, 1, and -2 when I subtract 9. Good. Question is, why did invert matrix did not work? This is you have zeros on this side, so you're not getting the ABC stuff you're used to. This is not the same as solving systems. What you're used to. These are dependent systems. So the method you know doesn't work here. You have to follow what I'm doing. You have to do the same thing. Times ABC. Your method is to calculate this. My method is calculating this. Now, just we'll have to fix it later. I have to finish this so to move to the next class. So I can divide this one by 2. So I have -4a plus 2b plus b plus c equals 0. 2a minus b minus 2b plus c equals 0. And 2a plus b minus 2c equals 0. You can remove any of the variables to reduce the system. You can multiply by 2, kill off a's. So a's are gone. That's -4 plus -3b and 2c plus 3c equal to 0. And a's are gone. 3b minus 3c, yes, equal to 0. So if you divide by 3 both sides, you get the system -b plus c is 0 and b minus c is 0. So b equals c equals 1. That's good enough. And now you can bring that into one of the equations up there to calculate your a. So if b and c are 1, that's going to give you 2, so a better be a half. So -4a plus 1 is 0. -4a is -2. A is a half. So another eigenpair. lambda 3 is 9, and a corresponding vector v3 eigenvector is 1/2 1 1. So finally we have all three eigenpairs, and I put those eigenpairs together into a single solution. X of t is equal to C1 eigenvector e to the 0 lambda as 0 t plus C2 second vector e to the, I believe it was 6t, plus third vector, which is 1/2 1 1, e to the 9t. Oh, I forgot C3 in front. There you go, C3. What was my first eigenvector? It was -4 1 1, and this one was 0 1 -1. Was it? Yep, 0 1 -1. Cool. Now e to the 0t, that's just 1. So what is my x of t? X of t is, well, actually let's list them all separate. So x1, it's not a vector anymore. x1 is -4c1. 0 will kill this term, plus 1/2 c3 e to the 9t. x2 of t is just a c1 plus c2 e to the 6t plus c3 e to the 9t, and x3 of t is a c1 plus, no, minus c2 e to the 6t plus c3 e to the 9t. That's the general solution. You can have initial conditions, you can check the Wronskian, right? All of the stuff that we did earlier. You solve linear systems using eigenvalue method, where you find eigenvalues using the equation up there with the determinant of a minus lambda I, and then you find corresponding eigenvectors, and then you will put everything together into a single solution, and then if you have the pairs you can check pretty much everything else. And that concludes part 1 of this lecture, because I need to go part 2 for complex. So Friday we're going to go into complex solutions, and obviously I will give you another update on exam grading on there. So 5.3, and then I think we're talking about solution, gallery of solutions. So we will be talking about solution curves 5.3 afterwards. That's a little bit shorter section, which is more of the analysis of the solution and what does it look like on the graph. You know, remember those solution curves like what is the name? Escapes you now. The little lines. My brain is not working anymore. Vector field. I can't. It's just I'm just done. I'm going to do some algebra equation solving now. See you Friday 11. Bye.